Okay, so today we're going to talk about this very simple Hello World program that is classical for all guys who produce some programming. And so we would talk a little bit about 6502, what it is. We will talk about its instruction set, and we will take a look at this Hello World example on a kind of a really bare metal, because there is not so many so much hardware and software on this to run it, and some very Q&A sessions. So we planned this session for like 35-40 minutes. Okay, so what do we know about the 6502? So it was presented in 1975. It can run at clock like 1 to 3 megahertz. And it was used in many computers like a BBC Micro, Apple I, Apple II, Nintendo NES, Commodore 64, and so on. And you guys know it for sure. It's an 8-bit CPU, and it's 16-bit address bus, so it can address up to 64 kilobytes of RAM. In general, RAM and ROM, so memory. And yeah, and here's a picture of SmartyKit board where you can see like address bus is A0, A15, so it's 16 lines there, and D0, D7, 8 bits for data bus. And also on the left, you can see like this 1 megahertz clock that is used as a clock generator for 6502 we use in our version of Apple I. So what is inside? It was very simple. So it's like 3,000 transistors inside. Now, as all we know, it's like billions of them on the chips, like used in CPUs and in modern computers, and like smartphones, even our iPhones have like almost 10 billion or 13 billion in the last versions. So it's very dense right now, but that time it was very simple because it's just a few years after the first CPU was presented, this Intel 4004. So it was just the beginning. Okay, what like quick recap what it is, what is CPU. So it is very simple. So CPU is basically, we can say it like this, that CPU is some chips, some piece of hardware that executes programs. And what is a program? Program is a set of instructions for this CPU. Because once the idea of the first CPU was to stop designing its own hardware for different sorts of devices like calculators. Well, once people decided to update software because it's easier than to redo all this big cycle of development and production with the chips. So they decided to make some kind of a universal chip that can execute different sorts of programs. So it could be used in different devices. So you can mass product these CPUs, universal chips, and then you can customize them using software. And this was a very good idea, and it was a real revolution, because after this we see how fast it developed. But basically all the CPUs from the 70s and from the modern time, they have like 3 main buses, like address bus to communicate with the memory, a data bus to exchange data with this memory, and control bus. Here I just like put like read and write. It's a little bit of it's more of different sorts of signals, but very basic is like CPU needs to say whether it wants to read or write, and that is the bare minimum it needs to have. Okay, here you can see the 6502 schematics. It's electrical scheme of how it should be connected, and you see the same address bus and data bus, and also control bus is presented by signals like ready, interrupt request, non-maskable interrupt, NMI, for example, and also reset that is connected to reset button, and read and write. Here it's RW. It's one signal, and in order to have the read signal, we need to to NAND it with a phi2, that is here pins 39. So basically, it's very simple. It has like 40 pins, and but it can do a lot, as you've seen in computers like BBC Micro, or played all of us probably played Nintendo NES. It's a lot of fun games was there. Okay, here's like the very beautiful board made by Roald Dahl from Bletchley, where Alan Turing worked. So here is its Apple I board, and here you can see, like in the section A7, you can see this CPU 6502 on the original Apple I board. It's beautiful, so I like to show this board. Okay, yeah, but what kind of instructions? We said like CPU executes some instructions, but what kind of instructions is this? Basically, all these CPUs, they have some types like this. So it's some arithmetical and logical operations. So it's like processors need to multiply, add, subtract, divide. The first ones for sure they wouldn't they didn't have any kind of floating point calculations, but right now they do. And also the first CPUs, they don't really have division, and you need to implement it in software. Also they have logical operations with registers, the inner memory, so they can rotate they can invert it and do different sorts of Boolean algebra operations. Okay, so the first part is needed. It's needed for calculations, and the first idea, the first thing that was like the first purpose of computers was calculations, because it was, as you know, maybe it was a lot of tasks like calculations for different sorts of rockets and all this stuff. So it's a lot of differential equations that needed to be solved, and so mankind tried to use these devices to speed up the process. And like one of the first things that was done on the first computer ENIAC was a calculation of pi with very, very high precision. And the second type of operations is read and write to memory and or input-output devices. It depends on the model of the CPU, because some CPUs, they have like I/O devices as a separate inputs, outputs. It's not part of the address space. Like Z80, famous CPU Z80 is like this, but 6502, it has the solid, I would say, memory space. So just all these input output devices is just part of the memory segment inside the big one. But anyway, so CPU to work, it needs to save and to get some instructions from somewhere. So it is memory, and it needs to have these instructions coming in, to execute them, and also it needs some data to process these numbers with which it should be working, some charts also. Yeah, so everything is stored in memory, so it needs to read and write there. The third big type of commands is jumps and branching, because one of the very powerful thing for computers is that they can do loops. People don't like loops, frankly. If you say like you do your chores like every day at 7 p.m., you would say, oh my God, I don't like it every day, every single day. But for a computer, it's just, wow, it's cool. It's the same. You don't need to invent anything. You just can crunch, do the same every day. And it's very cool. And so in order to make loops, you need this conditioning conditions. You need to check condition and branch. If, for example, if condition is not met, you can go back to loop. If it's like, okay, you can go next. And also there's jumps when you don't need any condition, you just go to some specific place because some instructions, they're not just like in sequence. And also very powerful thing that is a kind of a, I would say, pillar for all the software development industry right now. It's the functions and subroutines calls. And it's very cool because when CPU can do this, so one programmer could write a kind of a library of functions, and the other guys, they don't really know what exactly he wrote, but they can use it, they can call it, and they can call it and use in their programs. And so after this concept was like a kind of a multiplied many times, now we have the software industry where you can have like windows with like millions of lines of code with different sorts of AI, I don't know, ML libraries, and we just like use them. We have a lot of libraries for web development, different sorts of frameworks, and the key idea is the same. Somebody wrote something and we can just call this subroutine. And so CPU, even the simple one, it can do this because this is the very fundamental thing. And if we take a look at a 64 instruction set, so every instruction is encoded by 1 byte. And so here we can see in the table, it's so-called high nibble and low nibble. Nibble, it's 4 bits out of 8 bits from 1 byte. So it's like the lower and higher part of 1 byte. And so we can see, so in general, like it would be the question to the audience. Let we check our chat. Let me share and return back to. And I would return back to our, and the question is, how many instructions could be encoded by an 8-bit or 1 byte instruction? How many? Just to add some interaction to our session. Yep. Yeah, so it's like 256. Yeah, the maximum possible number of operations. And let us go back to the presentation. Yeah, but so as you can see here, like this instruction set, like the number of these instructions is less than 256 because we have empty spaces here. So it's a lot of instructions that have different opcodes, but operation codes because they have different addressing mode. We wouldn't touch this today, but it's less. It's like 70 to 80 instructions at all, but they with different types of addressing modes. They made up something like 160 or more than a half of 156 operation codes. But to make very simple application or program, we don't need so many instructions. So here you can see what we exactly would be using. So we would need to loading to register. So as we know, register is a small inner memory cell inside CPU that is used very fast and is accessible from for different sorts of operations. Some operations could be done only with registers inside. They couldn't be performed right in the memory. So here we use LDX, so we load to A register and load to X register. So we have here branch on equal for creating loops. So we would check if the current result is in A is equal to 0, which means in our case the end of the string. So in this case, we would need to branch to quit our program. Calling a function or subroutine. In our case, it's jump subroutine, JSR. We use Steve Wozniak's operating system function to print one char. And we'll talk about this later. Regarding arithmetic, we just need an increment X register, so it's in I and X, but it's arithmetics, and also we use with an unconditional, non-conditional jump. We just want to quit, and we need to go to the entry point of Woz operating system, so we use jump. Okay, let's take a look in general. What is hello world? It's very simple because in high-level languages, it's just one line. We'll print and hello world, and that's it. But if you just like zoom in, and you would understand that we would need some setup for this. For what do we exactly need? We need to have a null-ended string in memory to print. So we need to store it somewhere. In our case, we store it in read-only memory. So we kind of hard code it in there. And we have some address starting point where this string is located. And then we use this in order to collect chars, char by char, from array. And so this is the first part we need. The second, we need to have this loop that would print every char until we see the end, the 0 at the end. And so we need to check, is this char 0 or not? If not, so print it. If 0, yeah, so stop it. That's it. And go back to the operating system, so quit, exit. We need some function that really actually prints something on screen for the user. In our case, it's a Woz operating system echo subroutine. So it has specific address, and it could be called using this address. And also we need to quit somehow when this string already just is printed. So we need to do something next. And in our case, we just quit and go to reset. So it's entry point of Woz os, and that's it. So here's zoom in, and what do we have here? First of all, and let me also check what we have here. Okay. In order to follow, it's maybe easier for you to open up your own version of this. Okay, so it would be for you, it would be easier to follow. Okay, and okay, let me go back to this example. Okay, what do we have here? So line number 5, it's LDX 0. So we load value 0 to x. So we initialize x in order to use it as a counter. So as we write in C, for example, like int e equals to 0. That's it. So before we start the loop, then we start the loop. It's called print char, and it starts from line 6 and it goes right to line number 11. And so first of all, we load, we have this label called hello world text, and you can see it's on the line number 15. So it is located somewhere in ROM. So it has some specific address, like, and it starts just with bytes. So we first of all, we have 0D. What is 0D? 0D, it's a carriage return. So we want to have like the first line, to clear the first line. Then we have like this hello world text. Then we have, again, we have a carriage return. In our case, we have this, the second string, this is SmartyKit. And then we have 2 carriage returns. And right at the end, we have 0, 0, which shows that this is the end of the line. And in this place, this algorithm should stop. And what LDA with this label index does. So it uses hello world text as a pointer to this string, and it adds up x, the current value of x register, in order to load the value to a register inside. So it's a kind of a just very simple expression that we have in C. For example, it loads just array using some index. So index here is x, and array address is hello world text. Okay, so we have loaded some value to a. In the next, we have this branching BQ that just checks if a is 0 or not, because if a was 0, so it was so it set up the flag that is used by BQ in order to perform this branching. So if it's 0, it goes to end print, that is line 12, and then it goes to reset, and that's it. But if it's not, it goes to the next line, line number 9, and it calls GSR echo. So it's was varying system routine, and it uses values stored in a register in order to print it to the screen. So we have it already there, because BAQ it doesn't change a register. So we have this char already there, so it goes there. Right to the echo, and when this char is printed, what do we need? We need to increase our index. So it's like, as usual, we write something like I++ in C. Here we just like increase x, so we go to the next index. And so on the line number 11, we jump to the print char, so we go back to the loop, and then it starts over again with the x already increased. So we go to the next char, and that's basically it. So it's very simple. So we have this very simple loop, and it could do it. Very simple thing. And here it is. You can see on this slide, you can see how it works. For example, using this POM emulator, there is in a video. You can load this SmartyKit ROM from our GitHub, already built in ROM file. You can load it and then run fd00 or r means run. And so you can see a hello world. This is SmartyKit. So in uppercase, because Apple One worked with that uppercase. And so you can download this make file and all this ROM development folder from this link I've shared with you, and you can modify this assembler code to add some different sorts of strings modifying this hello world example, then you can build it and load to this POM, and you can run it even in emulator and check how the 6502 really works. So it's almost everything for today. Do you have any questions? If you have, you can just turn on camera and you can use your mic. Okay. If you don't have any questions, I can show you some beautiful pictures from my presentation to finalize it.
Are you running a series of these, just sort of building this up?
Not to show it to you because we have these pictures. This is my daughter. She's assembling SmartyKit. She likes it. And we use this original Apple I instructions recreated by Armin from Germany. And they're really beautiful. Also, we have this Apple I Unibody Workshop Edition. And also you can see here this text on the screen. So it's ASCII art. And now we have also the Steve Jobs and Steve Wozniak garage, where they assembled the first Apple I's, and we're gonna upload this to our GitHub. So everybody who has our kit, you could update your drivers and you would have this fun splash screen in your own SmartyKit. And also you can customize this, made with love by, here's like Steve Wozniak. You can put there your name or your kid's name. And it's not so hard to do. If you would have questions how to do it, just drop me a line. I can help you with this. Yeah. So if you don't have it, so you can pre-order, subscribe. We have Twitter, we have GitHub, we have YouTube, and we're gonna add a lot right now because we work hard for the new production batch in this year, and also we plan to optimize our line instructions, our website, everything to make it really fun and really geeky 8-bit experience, wiring and playing with this and having fun with the ASCII art, and just have real fun with you, with your family. For example, if you would like to show this to your kids and to spend time with them as a family project. So would love to answer some questions. You can ask it right now. You can join this Discord channel and ask something offline. Share your experience with 6502 or something like this. I would be happy to hear from you guys. Thanks, Mark.
Are you running more of these, sort of building up on the basic work you've just shown here?
So anybody wants to show up on camera for a screenshot, so that we at least we were together. If not, I just do it like this. So thank you, guys. We have this webinar on a weekly basis. So if you have friends who wants to learn something about 6502 and some coding basics with these pointers, functions, and so on, just share a link with them. Thank you, guys. It was my pleasure.